So we're starting the next unit. It is on energy and momentum. Our first topic is work. In your textbook, this is section 4.1. Now, when we talk about work in physics, it's a little bit different than the work that we talk about kind of like in our everyday lives. Work in physics is when we transfer energy to an object. So lifting something up off the ground, that's a transfer of energy. Pushing something and having it move, that's a transfer of energy. So that's the work we're talking about in physics. So I'd like you to copy this slide down. It says that work is when energy is transferred to an object when a force acting on the object moves it through a distance. And work is a scalar quantity. So we do not associate direction with work. So also, when we're looking at work, we're only interested in the force that is acting in the direction of the movement. So here we have a person kind of pulling at a crate using a rope that's angled. The only part of their of the force that they're applying that does work is the Fx in this case. So that Fx, which is F times cosine of theta, that is acting in the same direction as the motion. The F sine of theta is perpendicular to the motion. That F sine theta does no work because our crate is not moving up. It's only moving to the right. So that gets us to this equation here. You can copy this as well. When we're looking at work and the force is applied at an angle, the work function would be work equals force times displacement times the cosine of theta. Now, let's look at a problem here. It says an emergency worker applies a force of 16 newtons to push a patient horizontally for 2.5 meters on a gurney with nearly frictionless wheels. So what is the work done in this case? Now, I have a force of 16. The movement done is 2.5 meters. And this is being done at an angle of 0 degrees. So cosine of 0 is 1. So my work done is 40 joules. So now let's say that he's pushing this person, and the floor that they're on is angled at 25 degrees below the horizontal. So that would be 16 times 2.5 times 25 cosine, and I have 36. Now I have 36.25 and so on. Because if I go back to my original question, my significant digits are 2. I have to report my answer as 2, so I have 36 joules. Here's another situation, a woman pushing a lawnmower. The angle the lawnmower makes is 35 degrees. The force is 150, so 150 newtons times cosine of 35, and we have to also multiply by the amount of trips done, which is 10 times 2 times 15. So we have 36,861. I have 2 significant digits in the original problem. So 150 has 2 significant digits. 10 is 2 significant digits. We always take a minimum of 2. At least you'll do that in this course. And that rounds to 37,000. And we can, once we have something that is over 1,000, it's best to write it in significant figures. So 3.7 times 10 to the 4 joules. So the situations we talked about were positive work situations. Positive work is when the force and the displacement are in the same direction. When we have positive work, the object's energy increases. So this energy increase can be represented by either a speeding up or a height increase. So the force is applied in the right direction in this picture we have here. The motion of the cart is in the right direction. We could also have negative work. And this is when the force and displacement are in opposite directions. This is also when an object's energy decreases, it slows down. So in this case here, a person's trying to pulling to the left, but the motion of the cart is to the right. Now, the most common type of negative work you'll see is friction. So friction is always an oppositional force. It's always opposing motion. So if I have an object that is sliding, the force applied to it by friction will be in the opposite direction to where it's sliding, but it will move in the direction it's sliding. So negative work is done in that case. Now, anytime, again, just to remind you, anytime you see the large capitalized bold letters there, those are things you should copy down. So I would recommend you copy down this note and the one on the previous slide. Let's look at some negative work using friction here. So we have a toboggan. The mass of the toboggan with the children is 100 kilograms. It reaches maximum speed at the bottom of the hill, and then it glides 10 meters along a horizontal surface before coming to a stop. And the coefficient of kinetic friction between the toboggan and the snowy surface is 0.1. So the next slide is going to show us the free body diagram of this. The only force that's applied in the direction of the motion is the force of friction. The Fg is equal to the Fn, so the net force is equal to Fk or Ff. So in order to calculate the kinetic friction, it would be our Fg, or rather our Fn times mu, which is 0.1 times 100 times 9.8, which gets us to 98. So 98 newtons is the force that's applied. Now the toboggan slides 10 meters, so 98 times negative 10, because we're going 10 meters in the opposite direction, gives us a negative 980 joules worth of work. We could have also done this the other way. The sled slides 10 meters, and we can multiply that by a negative 98 Newton force, because that's in the opposite direction of the motion. We get negative 980 joules. So why is that work negative? It's because the force and the displacement are in opposite directions. Simple as that. There's also situations where zero work is done. This is an image here of somebody holding a toolbox on their shoulder. Even though he's applying a force to hold this toolbox up, the toolbox is not moving. It doesn't move left or right, up or down. So the force is non-zero, but the displacement is zero. So our work is zero. Another situation where we have zero work is when we have motion, but no force applied. So there's an air hockey table. An air hockey table is an example of this. If you can imagine an object in space, this could be an example of this as well. So let me talk about the space example. If we have an object that's flying through space, and it's far away from any sort of effect of gravity, or large effect of gravity, because everything would act on it, that object would be moving, but no force would be applied. So the work done on the object would be zero, because our force is zero. In another situation, we could have movement, but the movement could be perpendicular to the force applied. Here's a skater, and he's holding another skater up. He's applying a force up, and he's skating horizontally. The work done by his muscles pulling up on the skater is zero, because it's perpendicular to the motion. The positive work would be by his feet on his skates. So here's our situation where we have zero work. Please copy this down. It happens when the force is zero, when the displacement is zero, or when the force and displacement are perpendicular to each other. Here's another situation. We have a student pushing against a tree. The tree doesn't move, so the displacement will be zero. There's a few other examples like this. I won't go through them all. Just read those on your own. Now, I will go through this last problem with you, and this will end the lecture. So it says almost all real-world examples of work involve friction plus other forces. In summary, when analyzing the total work done on an object, all forces that are present, including friction, must be considered. The net effect of these forces can either be positive, negative, or zero, or have zero total work done on the object. So here's a problem. Now we have a hiker who's pulling a sled. He's applying a force at an angle. The force of friction is opposing the motion. And the values are given there. Please look at this slide. I'm going to just switch to my my camera here. And basically what we have is a situation like this. Let me just slide this over so that I can see. So our free body diagram would look something like this. We have a force of friction, and we have an FG and an FN. And we have this angle here, this angled force, but I'm going to put it into components. So I'll call it FAX, and also over here going up we'll have an FAY. FAY doesn't come out very good. So given that information, let's calculate what our FF is going to be and what our FAX is going to be. So FAX is 135 cosine of 48 degrees. Leave that there. F is going to be mu times Fn. And Fn in this case is going to be a bit more complicated. So we have Fn being equal to our Fg minus our Fay. So that is mg for Fg, and Fay is 135 sine of 48 degrees. I should also substitute these values in, I suppose. So mu is, in this case, actually, it says that we already have a constant force of friction. So I guess we could just say this is 67.0 Newton. My apologies, I just read the question again, and see that's how it is. So that simplifies things. But this is why you would notice that your FF wouldn't just be mu of Fg. It has to be mu of Fn, which is a little bit less than Fg in this case. So now we have our force of friction, we have our FAX, so our F net is FAX minus FF, that's 135 cosine of 48 degrees minus 67. Using the calculator, I end up with 135 times 48 degrees cosine and minus 67. I end up with a value of 23.333 newtons. That's my net force. And I need to find the work done by the hiker, by the friction, and on the sled. So, work done on the sled, this whole thing has been moved 345 meters. So the work on the sled is the force of the sled, which is 23.333 times 345. So this value times times 345 gets us to 8,000. Now I'm going to report this with two significant, actually it should be three significant digits. Each of those values does have three significant digits. So I'm going to report this, and one of the things you might notice is the degrees are 48 degrees. When you're calculating significant digits, you do not include the degrees in your significant digit calculation. So reporting this for 3 significant digits gets me 8.05 times 10 to the 3 joules. That's one answer. Now I need to find the work that the hiker does. This is going to be my force that the hiker applies in the direction, which is 135 cosine of 48, multiplied by the distance of 345. So this is let me just get the calculator here, 135 times 48 cosine times 345. And I'll round this to 3.12 times 10 to the 4 joules. That's the work of the hiker. And the work of the friction is going to be my force applied by the friction, which is negative 67 newtons, because it's in the opposite direction of the motion, times 345. 67 times 345, I have to make sure that that is negative. This is going to be negative 231. Decimal goes here, times 10 to the 4 joules. That's how I would calculate each of those. Now, another way to calculate work and energy is through the use of a force position graph. Now, with a force position graph, the area underneath the curve represent the work that was done. So sometimes we have force position graphs for certain devices. Springs are common. If you ever look at the data sheet for a spring. So since work is defined as the product of force times the displacement over which the force acts, then work must be equivalent to the graphical area underneath the graph of force versus position. So this is something else to be aware of, and I'll go through a quick little example here. So we have a piecewise graph here, force position piecewise function. And we're asked to calculate the work done between 0 and 5. So we have two geometric shapes here. We have a 5 by 6 rectangle and a 2 by 5 triangle. So it's 2 because 8 minus 6 is 2. So that's 2 times 5 divided by 2. That gets us to 35 joules done from 0 to 5. Between 5 and 8, we have a 3 by 6 rectangle, so that's 18 joules. And between 8 and 10, this is a 2 by 6 triangle. So we have 6 joules that are done. And I have to report that with 2 significant digits, so it's 6.0 joules. The total work done between 0 and 10 is the sum, oops, sorry, let me redo that, is the sum of the work done between each section. So the area under everything, which is 59 joules. So try out the homework problems for this unit and or for this section. Let me know if you're having any trouble in the class discussion board.